Hi, good day everyone. Uh, in this presentation, we'll discuss more about cost-driven design optimization uh, on the engineering economics. So, as we have discussed in the previous presentations, engineers must maintain a life cycle viewpoint as they design products, processes, and services. Such a complete perspective ensures that engineers considers initial investment costs, operation and maintenance expenses, and other annual expenses in later years. And of course, environmental and social consequences over the life of the designs. In fact, a movement called Design for Environment, or also known as green engineering, has prevention of waste, improved material selection and reuse, recycling of resources among its goals. Designing for energy conservation, for example, is a subset of green engineering. As we can see, engineering design is an economically driven art. So in this presentation, we'll discuss the main tasks for cost-driven design optimization, what what is the general approach for optimizing a design with respect to costs, and we'll illustrate the importance of cost-driven design optimization through an example. Examples of cost minimization through effective design are plentiful in the practice of engineering. Consider the design of a heat exchanger in which the material and configuration affect cost and dissipation of heat. The problems in this selection, designated as cost-driven design optimization, are simple design models intended to illustrate the importance of cost in the design process. These problems show the procedure of determining an optimal design using cost concepts. We should also consider discrete and continuous optimization problems that involve a single design variable, let's say x. This variable is also called the primary cost driver, and knowledge of its behavior may allow a designer to account for a large portion of the total cost behavior. For cost-driven design optimization problems, we have two main tasks that we need to do. First, we should determine the optimal value for a certain alternatives design variable. Okay, so that's the alternatives design variable. And next, we should select the best alternative with each with its own unique value for the design variable. For example, in number one, what velocity of an aircraft minimizes the total annual costs of owning and operating the aircraft? Okay. Next, for the second task, for example, what insulation thickness is best for a home in Virginia? Is it R11, R19, R30, or R38? So in general, the cost models developed in these particular problems consist of three types of cost. We have discussed cost terminologies in the previous lessons. So we have number one, fixed costs. Second, costs that vary directly with the design variable. And third, costs that vary indirectly with the design variable. A simplified format of the cost model with one design variable is shown in this formula. That is, cost is equal to A times X plus B over X plus K. where A is the direct varying cost, B is the indirectly varying costs, K are fixed costs, and X is the design variable in question. In a particular problem, the parameters A, B, and K may actually represent the sum of a group of costs in that category. And the design variable may be raised to some power of either directly or indirectly varying costs. It depends on the problem. So, we have here the general approach for optimizing a design with respect to cost. Okay, so first, we should identify the design variable that is the primary cost driver. This step is very important. Next, we should write an expression for the cost model in terms of the design variable. Third, we should set the first derivative of the cost model with respect to the continuous design variable equal to 0. So this is in calculus, we are going to solve for the maxima. For discrete design variables, we shall compute for the value of the cost model for each discrete value over the selected range of potential values. Fourth, solve the equation found in third step for the optimum value of the continuous design variable. Next, we shall use the second derivative of the cost model with respect to the design variable to determine whether the optimum value found in step 4 corresponds to a global maximum or a minimum. So, getting the second derivative, as we recall, gives us the point of inflection of the curve. Um, Whenever the curve is going up, the second derivative will determine the maximum value. Okay, and also there is a minimum value that is determined by the second derivative of the cost model. Okay, so this is the general approach in optimizing a design with respect to cost. So let us illustrate this through the next example. Example: the cost of operating a jet-powered commercial passenger-carrying airplane varies as the three halves power of its velocity. Specifically, with this formula, the operating cost, C sub O, is equal to a constant n v to the three halves, where n is the trip length in miles, k is a constant of proportionality, and v is the velocity in miles per hour. It is known that at 400 miles per hour, the average cost of operation is $300 per mile. Again, it is known that at 400 miles per hour, the average cost of operation is $300 per mile. The company that owns the aircraft wants to minimize the cost of operation, but that cost must be balanced against the cost of the passenger's time. Okay, so there is a passenger's time that is should be maintained or minimized, okay, which has been set to $300,000 per hour. The questions are: first, at what velocity should the trip be planned to minimize the total cost? It is the sum of the cost of operating the airplane plus the cost of passengers' time. And next, how do we know that our answer for the problem in part A minimizes the total cost? So these are the questions that we should answer for this particular problem. So going back to the approach that we described earlier, this is our solution. So we know that the total cost is equal to the cost or operating cost plus the passengers time cost. So that will be KNV to the 3 hubs plus 300,000 per hour times N over V, where N over V is time, of course, right? So N is miles and then V is miles per hour. Now, we solve for the value of K. We know that C sub O over N is equal to KV to the 3 halves. This is our given formula. Okay? So that will be $300 per mile is equal to K times 400 to the 3 halves. So it was described in the problem that at 400 miles per hour, the cost or the operating cost is $300 per mile. Okay, so that is also given in the problem. So with that, the value of K is equal to 0.0375. Therefore, if we are going to substitute the value of K in our total costs, right? We now have the total cost or the equation of the total cost equal to 0.0375 N V to the 3 hubs plus 300,000 times N over V. This will be our model for this particular problem. The next step or the third step in our general approach is to get the first derivative of our model. So the first derivative is 3 halves times 0.0375 NV to the 3 halves minus 300,000 N over V squared. And we should equate it to 0 to get either the maximum or the minimum point. Therefore, we can now solve for the value of V, right? Because for the first question, we are required to find at what velocity should the trip be planned to minimize the cost. Therefore, our V in this equation is equal to 490.68 miles per hour. And we can now check if this value of velocity is the right answer for our uh, first question. So to confirm, minimum cost solution with the velocity of 490.68 miles per hour, we then get the second derivative of our cost model and equate it to 0. Okay? So for if b is equal to 0, then the second derivative must be greater than 0. So the company concludes that a velocity of 490.68 miles per hour minimizes the total cost of this particular airplane's flight. So with that, to summarize our presentation, again, engineering design is an economically driven art. As described or as illustrated in our example, we can minimize the cost of an airplane flight by understanding the behavior of costs of operating this aircraft. Okay. Then we discussed the tasks involved in optimizing costs. We have presented the general approach in this design optimization, and we have illustrated cost-driven design optimization in this particular aircraft problem. So with this, Uh, if you have questions, just let me know. Okay, we'll move to the next lesson, which is present economic studies. Okay. Thank you.